So as we're moving forward with derivatives, so far we're familiar with this formula, right? So as x approaches c, so as x gets closer and closer to our defined c, we're tricking that slope formula into taking the slope at one point, whatever our c is. But with this idea, if I want to know the slope at 2, crank through the formula. Then I want to know the slope at 3, crank through the formula. What's the slope at 5? Crank through the formula. We don't want to do that every time. So there's actually, we could use this, but there's also a second derivative formula that is going to help us find the derivative or the slope at every point on a curve. Not just one point, every point. Okay, so I've kind of got a visual up here to kind of show. If this value right here, if this is x, and then I pick a point that is h away from x. So this is the x value, x plus h. Again, this distance between them, my change in x, is h. H is just some unknown distance between my two x values. As h gets closer and closer to 0, meaning this x plus h is getting closer and closer to x, we are again tricking our formula into taking the slope at one point. So as h closes, this is what this formula looks like. So this is the limit as h approaches 0. 0 is our change in x, how far apart our points are. So as they get closer to 0, the same point, again, f of x plus h, y1 minus f of x, y2, all over h. H is our change in x. This is the definition of the derivative of a function. So now, when we look to find the derivative, we can actually take the derivative of the entire function. And now if I want to know the slope at 2, boop, plug it in. Plug 3 in, boop, I know the slope. Instantly, I'm going to know the slope at a point because I know the slope at every point on that function. Okay? So that's kind of my intro. I'm going to come back with an example.